Welcome! In this session, we'll dive into LeetCode problem number 1448, count good nodes in binary tree. This is an interesting problem that challenges us to think recursively and leverage tree traversal techniques. Let's get started and explore how to solve it step by step. In this problem, we are given a binary tree where each node contains an integer value. Our goal is to count the number of good nodes in the tree. A node is considered a good node if, on the path from the root to that node, there are no nodes with a value greater than the node itself. Essentially, a good node is one where its value is greater than or equal to all the values encountered along the path from the root to that node. The input will be the root of the binary tree, where each node has a value and pointers to its left and right child nodes, or null if no child exists. The output will be an integer representing the total count of good nodes in the tree. To understand this, let's look at an example of a tree structure and walk through the reasoning step by step. In the first example, we have a binary tree with the root node 3, its left child 1, and its right child 4. The left child of node 1 is null, but it has a right child with value 3. On the right side of the tree, node 4 has a right child with value 5. Starting with the root node, we see that it is always a good node because there are no other nodes in the path from the root to itself. Next, node 1 is not a good node because the value of the root, 3, is greater than 1. Node 4 is a good node because its value is greater than or equal to all nodes in the path, which only includes the root. The right child of node 1, which is another node with value 3, is also a good node because its value is greater than or equal to all nodes in its path. Finally, node 5 is a good node because it is greater than or equal to all nodes in its path, which are the root in node 4. In this example, the total number of good nodes is 4. Now, let's consider a second example. Here, the root node also has a value of 3, with both left and right children having the same value of 3. The left child of the left node is 4, and the right child of the right node has children with values 2 and 5. Starting with the root, it is a good node because no other nodes exist in its path. The left child of the root is also a good node since its value is equal to the root's value. The left child of this node, with a value of 4, is a good node because 4 is greater than all values in its path. On the right side, the right child of the root is another good node since its value matches the root's value. Among its children, the node with value 2 is not a good node because its value is less than the root. However, the node with value 5 is a good node because it is greater than all values in its path. In this case, the total number of good nodes is 5. In the final example, we have a tree with just one node, which has a value of 1. Since it is the only node in the tree, it is by definition a good node, and the output is 1. Now, let's review the constraints and edge cases we need to consider. The number of nodes in the tree can range from 1 to 10,000, and the value of each node can be any integer between -10,000 and 10,000. Edge cases include a tree with only a single node, where the node is always a good node, and trees where all nodes have the same value, making every node a good node. For highly unbalanced trees that resemble a linked list, the algorithm must still traverse the entire tree and correctly compute the count of good nodes. Additionally, the algorithm must handle trees with negative values and compare them accurately to determine which nodes are good. These considerations are crucial for implementing an efficient and correct solution. To solve the problem of counting good nodes in a binary tree, we need to identify nodes that are not overshadowed by larger values along their path from the root. One approach we considered is a brute force solution, which involves performing a depth-first search while keeping track of the entire path from the root to each node. At every step, we compare the current node's value to all its ancestors to determine if it qualifies as a good node. While this approach is conceptually straightforward, it requires storing and repeatedly comparing the full path for every node, which quickly becomes computationally expensive. This leads to a time complexity of O(n) squared, due to the repeated comparisons, and a space complexity of O(n) to store the path and recursive stack. Given its inefficiency, especially for large trees, this brute force method is not practical for this problem. A more efficient approach to solving this problem is to use depth-first search with a running maximum. The key insight here is that we don't need to store the entire path from the root to a node. Instead, we can simply keep track of the maximum value encountered so far along the path. A node is considered good if its value is greater than or equal to this running maximum. Starting at the root, we compare each node's value to the running maximum, increment the count of good nodes if the condition is met, and then update the running maximum to the greater of the current maximum or the node's value. This process is repeated recursively for both the left and right children. The implementation is efficient, as each node is visited once, resulting in a time complexity of O, n. The space complexity is O, h, where h is the height of the tree, due to the recursive stack. This approach eliminates unnecessary comparisons, making it both faster and more memory efficient. The time complexity of the optimized DFS approach is O, n, as each node in the tree is processed exactly once. The space complexity is O, h, where h is the height of the tree, because the recursion stack at any point will hold at most one branch of the tree. Alternatively, we could solve this problem using a breadth-first search approach with a queue. In this method, we perform a level-order traversal, tracking the maximum value encountered along the path for each node. For every node, we update the maximum value as needed, and enqueue its children for further processing. While this approach avoids recursion, it introduces additional overhead from managing the queue. The time complexity remains O, n, but the space complexity can be O, n, in the worst case for very wide trees. Ultimately, the DFS approach is simpler to implement and avoids the explicit memory overhead of the queue, making it the preferred solution. The chosen strategy for solving this problem is the depth-first search with a running maximum, as it strikes a balance between simplicity and efficiency. By observing that we only need to track the maximum value along the path instead of storing the full path history, we significantly reduce both time and memory usage. This realization was a key breakthrough, transforming the solution into one that is scalable and elegant. Compared to the breadth-first search alternative, DFS requires less explicit memory management and aligns naturally with recursive tree traversal. Additionally, this optimized approach eliminates the inefficiencies of the brute force method, reducing the time complexity from O, n squared, to O, n. The aha moment here was recognizing that tracking just the running maximum is sufficient to identify good nodes. This insight allowed us to simplify the implementation while ensuring it remains fast and effective, even for large binary trees. To solve the problem of counting good nodes in a binary tree, we use a depth-first search, or DFS, traversal approach. Let's begin by understanding what makes a node good. A node is considered good if its value is greater than or equal to every node value encountered along the path from the root to that node. This means we need to traverse the entire tree while maintaining a record of the maximum value seen so far along the path. DFS is an ideal choice for this task because it allows us to explore each path deeply while keeping track of the maximum value efficiently. We'll use a recursive implementation in this case, as it simplifies the logic. The recursive function will take two parameters: the current node we're visiting and the maximum value observed along the path leading to this node. If the current node is null, this will be our base case, and will simply return 0. For non-null nodes, we'll check if the current node's value is greater than or equal to the current maximum. If it is, we increment our count of good nodes. We then update the maximum value to reflect the larger of the current node's value or the previously recorded maximum. Now, let's discuss how to traverse the tree recursively. For each node, we'll call the function on its left and right children, passing along the updated maximum value. The counts of good nodes from the left and right subtrees are then added to the count for the current node, if it qualifies as good. This ensures we account for all nodes in the tree. There are a few edge cases we need to handle. For instance, in a single node tree, the root is always good since there's no other node to compare it against. If all nodes in the tree have the same value, then every node is good because no node violates the condition. Similarly, for skewed trees, whether they are left-skewed or right-skewed, the algorithm still works correctly since it traverses every node regardless of the tree's shape. Once the traversal is complete, we return the total count of good nodes. The key insight here is that the maximum value along the path is what determines whether a node is good. By passing this maximum value during recursion, we avoid the need for additional data structures. The algorithm is efficient, with a time complexity of O, n, where n is the number of nodes in the tree. Each node is visited exactly once, and the maximum value is updated in constant time. The space complexity of this solution is determined by the recursive call stack. For a balanced tree, where the height of the tree is logarithmic in relation to the number of nodes, the space complexity is O log n. However, for a skewed tree, where the height equals the number of nodes, the space complexity is O n. The input to our algorithm is a binary tree, where each node contains a value and pointers to its left and right children. We rely on the recursive call stack to traverse the tree in DFS order, with the stack size being proportional to the tree's height. Let's consider the Python implementation of this algorithm. We define a helper function DFS that takes two parameters, the current node and the maximum value seen so far. If the current node is null, we return 0. Otherwise, we check whether the current node's value is greater than or equal to the maximum value. If it is, we count the node as good by setting a variable to 1. We then update the maximum value for the path to be the larger of the current node's value or the maximum so far. Finally, we recursively count the good nodes in the left and right subtrees, passing along the updated maximum value. After the recursive calls on the left and right subtrees, we combine their results, along with the count for the current node, and return the total count. This process continues until all nodes in the tree have been visited. The function goodNodes initiates the process by calling the DFS function on the root node, using the root's value as the initial maximum. Let's break down the key operations in this algorithm. First, at each node, we compare its value to the maximum value encountered so far on the path. This comparison is performed in constant time, O(1). Second, each recursive call corresponds to a node in the tree, and the total number of calls equals the total number of nodes, n. Finally, updating the maximum value at each step is also a constant time operation. With these operations combined, the algorithm efficiently traverses the entire tree. A few important edge cases to consider are, if the tree is empty, the function should return 0, as there are no nodes to evaluate. For a single node tree, the root is always good. If all nodes in the tree have the same value, every node counts as good. The algorithm also handles skewed trees, whether they are left skewed or right skewed, without any issues. Additionally, this algorithm works seamlessly with trees that have negative values. The comparison logic is strictly based on the values of the nodes, and negative numbers are handled just like positive ones. As long as we maintain the maximum value encountered along the path, the algorithm will correctly determine whether each node qualifies as good, regardless of whether the values are positive or negative. This makes the solution robust and applicable to a wide range of binary tree structures and value distributions. Here, we start by defining the treeNode class, which represents a node in the binary tree. Each tree node has a value and pointers to its left and right children. Next, we define the solution class and its method goodNodes, which will calculate the number of good nodes in the tree. Inside the goodNodes method, we define a helper function called DFS, which performs a depth-first traversal of the tree. The DFS function takes two arguments, the current node and the maximum value encountered so far along the path leading to this node. If the current node is null, we simply return 0 since there are no nodes to process. Otherwise, we determine if the current node is good by checking if its value is greater than or equal to max_value. If it is, we increment the count of good nodes by 1. We then update max_value to reflect the greater of the current node's value or the maximum value seen so far. Finally, we recursively calculate the number of good nodes in the left and right subtrees and add those to our count. The final step is to start the depth-first search traversal from the root node. We pass the root itself and its value as the initial max_value to the DFS function. The DFS function will then explore every node in the tree, count the good nodes, and return the total. This completes the implementation of the goodNodes method, allowing us to determine how many nodes in the binary tree are good based on the problem's definition. Here, we start by defining the structure of a binary tree node using the treeNode class. Each node has three fields, an integer value, a reference to the left child, and a reference to the right child. We also provide constructors for flexibility in creating nodes, allowing us to initialize a node with just a value, or with a value and its left and right children. Below that, in the solution class, we define the goodNodes method, which takes the root of the binary tree as input. This method acts as our entry point for solving the problem. It calls a helper method, DFS, starting from the root node and passing the root's value as the initial maximum value encountered on the path. This is because the root is always considered its own path starting point, so its value is the largest we've seen so far. The DFS method is where the main logic resides. It begins by checking if the current node is null. If it is, we return 0 since there are no nodes to evaluate. Next, we determine if the current node qualifies as a good node. A node is considered good if its value is greater than or equal to the maximum value encountered so far on the path from the root to this node. If it is, we assign 1 to the variable good, otherwise, it remains 0. We then update the maximum value for the current path using math.max, comparing the current node's value with the previous maximum. After that, we recursively call DFS for the left and right subtrees, passing the updated maximum value along. The results from these recursive calls are added to the good variable, ensuring we count all good nodes in the left and right subtrees as well. Finally, we return the total count of good nodes for this subtree. In the first example, we have a single node tree where the root node has a value of 3. We start a depth-first search, or DFS, at the root with an initial max_value set to 3. The root node's value is compared with the max_value, and since 3 is greater than or equal to 3, it qualifies as a good node. We increment the count to 1. Next, we update the max_value to ensure it remains the maximum value encountered so far. In this case, it stays at 3 because the current node's value does not exceed it. Since the root has no left or right children, the recursive calls for both return 0. Adding these results, the final count of good nodes in this tree is 1, which is the root itself. Now, in the second example, the tree has multiple nodes, and we begin at the root with a value of 3. Here, the initial max_value is again 3. Comparing the root node's value with the max_value, we find that 3 is greater than or equal to 3, so it is a good node. The count is increment to 1, and the max_value remains 3. For the left subtree, we move to the child node with a value of 1. Comparing 1 with the max_value, we see that 1 is less than 3, so it is not a good node, and the count remains 0. The max_value remains unchanged at 3, and since this node has no children, the recursive calls return 0. Thus, the left subtree contributes no good nodes. For the right subtree, we proceed to the child node with a value of 4. Since 4 is greater than or equal to the max_value of 3, it counts as a good node, increasing the count by 1. The max_value is updated to 4 as it is now the largest value encountered. Continuing with the right subtree of the node with value 4, we move to its child node with a value of 5. Comparing 5 with the max_value of 4, we find that 5 is greater than or equal to 4, so this node is also a good node. The count is increment by 1, and the max_value is updated to 5. Since this node has no children, the recursive calls for both left and right return 0. Therefore, the total good node count for the subtree rooted at node 5 is 1. Adding this to the good node count for the right subtree rooted at node 4 gives a total of 2 good nodes in the right subtree. Combining this with the root node, the final good node count for the entire tree is 3. The output is 3, representing the root, node 4, and node 5 as good nodes. In the third example, the tree is more complex and begins with a root node of value 5. Starting the DFS at the root, we set the initial max_value to 5. Since the root node's value is equal to the max_value, it is a good node, and we increment the count to 1. The max_value remains unchanged at 5. Exploring the left subtree, we move to the child node with value 4. This node's value is less than the max_value, so it is not a good node, and the count remains 0. The max_value stays at 5, and we proceed to the left child of node 4, which has a value of 3. Comparing 3 with the max_value of 5, we find that it is not a good node. Since this node has no children, the recursive calls return 0, leading to a total of 0 good nodes in the left subtree of the root. For the right subtree, we move to the child node with value 8. Since 8 is greater than or equal to the max_value of 5, it is a good node, and we increment the count by 1. The max_value is updated to 8 as it is now the largest value encountered. Looking at the left subtree of the node with value 8, we find a child node with value 7. Comparing 7 with the max_value of 8, we see that it is less than 8, so it is not a good node.
The count remains unchanged, and since this node has no children, the recursive calls return 0.
Shifting to the right subtree of node 8, we encounter a child node with value 9. Comparing 9 with the max underscore value of 8, we find that 9 is greater than or equal to 8, making it a good node.
The count is incremented by 1, and the max underscore value is updated to 9. Since this node has no children, the recursive calls for both return 0. Adding up, the right subtree of node 8 contributes two good nodes, nodes 8 and 9.
Combining this with the root node, the total good node count for the entire tree is 3, which includes the root, node 8, and node 9. The output for this example is also 3. The time complexity of our solution is O, n, where n represents the number of nodes in the binary tree. This is because we perform a depth-first search, or DFS, traversal, visiting each node exactly once. Each node is processed individually, and the operations per node are minimal. Specifically, we check if the node's value is greater than or equal to the maximum value seen so far, which is a constant time operation, O1. Similarly, updating the maximum value and making recursive calls to the left and right subtrees are also O1 operations. Importantly, these recursive calls don't overlap in their work because the left and right subtrees are distinct parts of the tree. When we sum up all the work across the entire tree, it scales linearly with the number of nodes, which gives us the O(n) time complexity. The space complexity of the solution is determined by the space used in the call stack during the recursive DFS traversal. This depends on the height of the binary tree, denoted as h. At any given moment, the maximum number of recursive calls on the stack is proportional to the tree's height. Each call uses O(1) additional memory for local variables like the current node, the maximum value, and the count of good nodes. Thus, the overall space complexity is O(h). Now, let's consider different scenarios. In the best case, where the tree is perfectly balanced, the height of the tree is O log n, leading to a space complexity of O log n. In the worst case, a completely skewed tree, where all nodes are either to the left or the right, results in a height of O(n), making the space complexity O(n). For an average binary tree, the height is typically proportional to O log n, so the average case space complexity is also O log n. To compare, a naive or brute force approach would involve traversing the tree multiple times. For each node, you would repeatedly traverse the path from the root to that node to determine the maximum value. This inefficient approach results in a time complexity of O(n squared, in the worst case for a completely skewed tree. However, our optimized solution significantly reduces this by maintaining a running maximum value during a single DFS traversal. This allows us to achieve a time complexity of O(n). In terms of mathematical justification, each of the n nodes is visited exactly once during the DFS, so the total number of operations is linear relative to the number of nodes. Similarly, the stack space required for recursion is proportional to the height of the tree, resulting in a space complexity of O(h). To summarize, this solution achieves O(n) time complexity and O(h) space complexity, with the space complexity being O log n for balanced trees and O(n) for skewed trees. This makes the solution highly efficient compared to the naive O(n squared) approach. When solving this problem, there are a few common mistakes that can trip you up. One major issue is not updating the maximum value along the path as you traverse the tree. If you forget to pass the updated max_so_far value to child nodes during recursion, the comparison for identifying good nodes will be based on outdated or incorrect data, leading to an incorrect count. Another mistake is confusing the global maximum value with the path-specific maximum. Remember, the condition for a node to be good depends on the maximum value along the specific path from the root to that node, not a global maximum across the entire tree. Misunderstanding this distinction can cause you to misclassify nodes. Lastly, it's important to handle edge cases properly, such as trees with only one node or trees containing duplicate values. Overlooking these scenarios might lead to runtime errors or incorrect outputs during testing, so always consider these cases in your solution design. Another potential pitfall is using a suboptimal traversal approach. While there are several ways to traverse a binary tree, this problem is most naturally solved using pre-ordered traversal because you need to evaluate whether the current node is good before exploring its children.
Using post-order or level order traversal could lead to unnecessary complications or inefficiencies. Additionally, some may make the mistake of introducing inefficient recursion or misusing memoization. For example, if you recalculate the maximum value from the root for each node instead of simply passing the max_so_far value down the recursive calls, you add unnecessary computation. This bloats the time complexity of your solution. By sticking to passing the max_so_far value directly, you can keep your implementation efficient and clean. Now, let's look at some insights that can help you approach this problem effectively in an interview setting. First, at its core, this problem is about comparing values along a path in the tree, making depth-first search, or DFS, a natural choice. Demonstrating clarity in how you handle recursion and pass parameters like max_so_far is a great way to showcase your problem-solving skills. This problem also highlights the importance of understanding path-specific properties in tree structures, which is a recurring theme in many tree-related problems. To optimize your solution, emphasize how your approach avoids redundant calculations, such as recalculating the maximum for each node. Additionally, interviewers might present follow-up variations to test your adaptability, such as asking you to count nodes with different conditions, like those smaller than all their ancestors, so be prepared to adjust your logic while keeping the overall structure of your solution intact. To deepen your understanding, it's helpful to explore related problems that share similar patterns or concepts. For instance, LeetCode 98, Validate Binary Search Tree, involves passing constraints like minimum and maximum values down the recursion, much like passing max_so_far here. Similarly, LeetCode 112, Path Sum, focuses on path-specific calculations using a recursive DFS pattern. LeetCode 1026, Maximum Difference Between Node and Ancestor, also deals with ancestor-descendant relationships in trees, which parallels the path-based comparisons in this problem. Finally, LeetCode 1372, Longest Zigzag Path in a Binary Tree, emphasizes recursive traversal techniques and path-based properties, making it another useful practice problem to strengthen your understanding of tree-based algorithms. There are a few alternative approaches to solving this problem, each with its own trade-offs. The optimal method is a pre-order recursive DFS, where you pass the max_so_far value as a parameter. With this approach, you check if the current node's value meets the good node condition, update max_so_far as needed, and then recurse to the children. This has a time complexity of O, n, and space complexity of O, h, where h is the height of the tree. Another option is an iterative DFS using a stack, where you store pairs of nodes and their corresponding max_so_far values. While this avoids recursion depth limitations, it requires explicit stack management, which can be more error-prone. Finally, a breadth-first search, or BFS, approach uses a queue to traverse the tree level by level while maintaining max_so_far. However, BFS is less natural for this problem since the good node condition depends on path-specific properties rather than level-specific ones, making this approach less efficient and more cumbersome to implement. Great job! We've successfully solved the problem using a depth-first search approach while tracking the maximum value along the path. Remember, understanding recursion and tree traversal is critical for problems like this. Thanks for joining us, and don't forget to like, comment, and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!